My presentation is Gradient Descent Demystified. Who am I? My name is Stu. I'm a machine learning engineer at Opendoor in San Francisco. I'm Stewart141 on Twitter and the internet generally. Opendoor, who are we? Opendoor is a startup that buys and sells homes online. Our mission is to make the home buying and selling process kind of worry-free for all Americans. Last week, we just raised $400 million from SoftBank, so that was great. And we have engineering offices in San Francisco, Los Angeles, and Atlanta. So definitely come and talk to me if you're interested in learning more. Great. So what we're going to do in this session is kind of puzzle through the gradient descent algorithm and really have in mind kind of a working prototype for linear and logistic regression. Gradient descent. Wikipedia, source of all truth, says gradient descent is a first-order iterative optimization algorithm, finding the minimum of a function. So to find this minimum, we take steps proportional to the negative of the gradient. OK, but what's a gradient? Khan Academy, another great source of truth, says that a gradient is a vector-valued function, a vector of partial derivatives. OK, so that's something we can work with. If we have a situation like this, I'm sure you've seen similar charts. If we have an optimization, the center of the circle is kind of like the lowest point, the optimal point. At each step of the iteration, we move against the gradient in the direction of the negative gradient until we approach as closely as need be to the center. So just a little initialization here. But let's look at an example. So imagine we have a formula, maybe just a simple parabola. X squared, x times x. We know what that will look like. It'll look like a parabola centered at 0. And there are a couple things that are interesting. So here we know what the kind of the optimal solution is. If we're trying to minimize this function, it's 0. And we don't really need any fancy methods to tell us that. But we're trying to kind of generalize this. So here we can just point and say, yep, minimum is at 0. But gradient descent gives us kind of like a more general framework for finding, perhaps in a messier function, finding this minimum. So we can also take the derivative of a function like that. And the derivative is just 2x, which is probably unsurprising. But the gradient then really is nothing all too scary. Here we could just say, well, the gradient is the partial derivatives. Here, it's a function of a single variable. So there's just one partial derivative. So we can just pack it in an array and be good to go. And I spilled the beans on this, but what we want to keep in mind is that's what we're trying to do. We're trying to be able to solve these arbitrary functions, ones where SymPy magic might not help us out. So step proportional to negative gradient. So if x is greater than 0, if we were looking at that parabola, if x is greater than 0, the derivative is always 2x. So say we're at the point 5, then the derivative would be 10, 2 times 5. And stepping in the direction of the negative gradient would take us in the negative direction. Now, modulo a learning rate is something we'll discuss later. We're in the positive domain, positive x domain. If we take a step in the direction of the negative gradient, we'll get closer to 0. Again, modulo this gradient or this learning rate. So that's great. So that's really promising. And again, if we're in the negative domain, then when we take the derivative, we'll be stepping towards 0. Exactly the opposite. So in both of these cases, it looks like stepping in the direction of the negative gradient is is looking promising. We have no guarantees yet, but we're on the right track. So now we'll do it live. So starting with linear regression, just a little initialization here. And the very first thing I'm going to do is introduce a bias term. I don't want to dwell too much on this, but this is akin to, if you have going back all the way to algebra, like y equals mx plus b. B is the bias. It's just a term that shifts a line, shifts a function away from kind of like the center. So here we're just going to use some ones. And in particular, we need 1 for every element of x. X is here just like a data matrix made by Scikit. This make classification is from Scikit. And we have 3 features. So we have kind of 3 random features and 1,000 rows, 1,000 data points. And here we're adding kind of a 4th feature, which is it's kind of just ones all the way down. So then we'll staple that onto our x. And just for making dimensions work well, we'll do that. So now, aside, do we even need gradient descent for this question? For linear regression, no. For linear regression, we have this data matrix, which is m by n, in our case 1,000 by 4 now, and we have this y, the true ground truth, which is 1,000 by 1. And there's this normal equation, the normal equation, which says y equals xb plus epsilon. Very similar, again, to y equals mx plus b. Y is, again, our m by 1, our 1,000 by 1 element, kind of like outcome variable. X is our data matrix, and B, these betas are what we're trying to learn through gradient descent. We're trying to, iteratively optimize these betas to minimize the distance between the right-hand and left-hand side of this function. If you solve here for beta, you'll get this equation. That can be done with, just a spot of matrix calculus or algebra. And it gives us a way, we can actually get at these betas without gradient descent. So if we try to copy that into code, we'll get something like that. And we can sanity check that. So sure enough, Scikit has a linear regression regressor. And we don't actually want an intercept because we kind of built in that intercept ourselves. That's what the bias column did. It's nothing more than the intercept. So we can get the coefficients from Scikit and compare them to what we just got through the normal equation. Hopefully they're the same, and they are. So that's great. It looks like the normal equation, as promised, is kind of doing what Scikit does, whatever that is. But where are the gradients? Right now we're really lacking in gradients, and we were promised gradient descent. So I guess the biggest spoiler is, so linear and logistic regression aren't very different to optimize. In particular, for linear regression, we're just going to use the identity function as a placeholder to make it kind of procedurally identical to logistic regression. And for logistic regression, we'll use the sigmoid function. So that's the identity function. It really does nothing. It just takes in an input and returns the input. And forgive the LaTeX typo there. There should be a line in the middle. The sigmoid function looks like this. This is kind of the sigmoid curve that you've probably seen before. So let's write them up. So the identity function, as we said, is really just takes something and returns it. That's pretty boring. Sigmoid function is actually available in SciPy as this xbit function. But let's also write it up for the instructional value. So just again copying from the equation we saw, that's what the sigmoid function is. And we can confirm that we haven't done anything crazy. Xbit and sigmoid should produce the same output, and they do. OK, that's perfect. But why do these equations matter? What's our hypothesis? So when we were looking earlier at the normal equation, we saw y equals xb plus epsilon. We can't really control epsilon. Epsilon is just mean zero idiosyncratic errors. But we can control x and b. X is given. So we're really just trying to optimize b so that xb equals, as close as we can, y. So our hypothesis is really xb, x matrix multiplied with b for linear regression. And for logistic regression, it's exactly the same. It's just that we're going to wrap that xb in the sigmoid function. So just recalling the normal equation, as we were just talking about, we really have just kind of identity, which does nothing, times x at betas, maybe the Scikit-learn betas. And then the shape of our hypothesis then is probably not surprising, but it has the exact same form as the y's, which is good. We should have one prediction for every row in our data matrix. Gradient descent, though, is an iterative optimization algorithm. First order here just means we're only taking into account the first derivatives. So when we were looking in SymPy at that parabola before, we took the first derivative, saw it was 2x. We didn't take the second derivative, which would have been 2. But here, first order is differentiating from something like Newton's method, where we might take into account the second order derivatives of our functions. But gradient descent works great with just the first order derivatives. So really the key here is iterative. We have to define some update step that gets us closer at each iteration to the final outcome. So let's do it. So we have an update step. It takes in betas and does something. And we have gradient descent. And so this gradient descent method is definitely going to need an x, definitely going to need a y. We need a learning rate, which we will touch on in just a minute. And we also need a kind, because we were promised linear and logistic regression. So with a kind parameter, a learning rate, the final thing we need is just how many iterations to take. So here I'm going to declare that this is a reasonable number of iterations for this problem, but certainly there are fancier approaches both for learning rate and iteration to find kind of optimal values. Okay, so what do we do? So we know we want to return betas. Great. So because this is an iterative optimization algorithm, it doesn't really matter where we start. We can start anywhere. And we'll just start at 0, just with a vector of zeros. So here, we have 4 features in our data matrix. We had started with 3 kind of made-up features, and then we added the bias term. So we're going to start with these kind of like 4 zeros. And we're going to multiply basically x by 4 zeros and check if it's equal to y. It won't be. We just made up zeros. But from there, we can iteratively improve kind of the spirit of the algorithm. So we don't actually want to just return the betas, though. We want to return the betas like modified. And in particular, what we want to do is pass the betas through an update step. And we want to do that iterations times. So this pipe method just takes the betas and pipes them through, basically calls update step iterations times on these betas. All right, so we do have a little bit of bookkeeping. So kind has to be either linear or logistic, or we're going to punt. So if we're given something else, we could say, whoops, do not support kind. And now we actually have to account for the kind. So we were looking at the identity and sigmoid functions earlier. So we're just going to use the identity function if kind equals linear. Else, we know we're in the logistic domain, and we're going to use the sigmoid function. So now this is actually starting to look like all we need, except this pesky update step. But we're actually in pretty good shape there too, because we know what we want to do. We want to return the betas minus some learning rate times the gradient. That's what Wikipedia told us to do. Okay, but what's the gradient? Well, I don't really know. But I do know our hypothesis. So our hypothesis, again, was that we're going to take this function, be it identity or sigmoid, and we're going to wrap that, wrap our x beta matrix multiply. And that's progress. So our loss then is just the difference between our hypothesis and the true y value. And I won't derive the next line here, but I will say that just like in the case we were looking at for the normal equation earlier, this is just like 4 lines of matrix calculus, or analogously, there's an algebraic solution to derive the gradient, and it happens to be just x prime matrix multiplied with the loss. I will give an intuition as to why this might be the case, though. So we know that we have exactly 4 betas. Our betas is a vector of length 4. And x prime, so x prime, x was 1,000 by 4. So x prime is 4 by 1,000. And the loss, we said, was 1,000 by 1. It's exactly the same shape as y. So if we take a 4 by 1,000 matrix multiplied by the 1,000 by 1 matrix, we'll get a 4 by 1 vector. And that's looking really promising, because the betas are a 4 by 1 vector. And here we're just scaling some other 4 by 1 vector and subtracting it off. So the dimensions work. And I think dimensionality, dimensional thinking in this case is a really great way to approach the problem. And oftentimes, like if I'm looking at matrices and I'm not sure exactly what's going on, it's a great get out of jail free card to just think, man, like what can I do? Like what's a valid matrix multiply here? And in this case, we found one. So if we take that kind of derivation of the gradient, we have kind of a method that looks reasonable. It's very small, but could this possibly actually do what we need? So let's check. So the betas here would just be the gradient descent method. And I do see one thing we're going to have to do is we're actually going to need to scale this gradient. And this isn't too important, but we're going to want to scale this gradient. Simply here dividing by 1 over, dividing by m, the length of the design matrix. This is just a normalizing factor. And now we can check. And we see, sure enough, that these gradient descent betas are exactly the same as the betas returned by the normal equation and Scikit. So that's all it really took. But does this work for logistic regression? Kind of, that's the more implausible one almost. We just slap this sigmoid function around, seemingly a linear regression derivation, and we're claiming it's going to work. So again, we have no need for an intercept. We've done that ourselves. And should be able to go ahead and fit. And then the logistic regression, for exactly the same sense, we just grab these coefficients off the scikit-learn estimator. And for gradient descent, now we can try with this logistic flag and hope that this goes well. So just for the sake of presentability, we'll round these. And it looks like the exact same code that works for linear regression is also perfectly applicable modulo this single function call to logistic regression. So that's a really good start. But now I have a bold claim. And I want to say that with just that little snippet of code, we're 90% of the way to having like a fully formed scikit-learn estimator that functions in all the same ways as kind of the linear and logistic regression estimators we were just pulling from Scikit and taking as canon. So let's try that. So if we have kind of the skeleton of a class here, we know that this predict method is going to take x and nothing more. This fit method is going to take x and y, and it's going to return self. But before it returns self, we actually have to tag the coefficient onto the body. Let's set up just like a gradient descent classifier regressor. It doesn't fit neatly into Scikit, being both that a classifier and a regressor, but that's really not a going concern here. So the init method is really the same init we saw earlier. So we'll need a kind here, linear. We'll need a learning rate. And again, this learning rate is a method to make sure that we don't diverge. So when we were plotting e earlier, say we started at point 5. If we just take the derivative, that being 2x, and then go negative 2 times the gradient, or so negative 2 times 5, or negative 10, we'll end up at negative 5. Of course, we can then jump back to 5 by going in the direction of the negative gradient, and we'll just keep ping-ponging back between 5 and negative 5 till the end of time. It's probably not quite what we need. The learning rate is a way to modulate this, is say, actually, we don't want to go back exactly all the way in the direction of the gradient. We want to take a smaller step, this being an iterative optimization algorithm, to make sure we don't overshoot. So there might be a local minima that's small, and we want to make sure that we don't have kind of that divergent behavior, going back and forwards until the end of time. So that's what this learning rate does. And we also are going to need the same iterations that we had before. So we can tag in some iterations here. And because now we're in a class method, we're going to have to do some post-production magic here to get everything set up. In particular, tagging them onto the body. Great. So now fit. So this is where all the work really pays off. So we already did everything we need for this estimator. That's just the gradient descent method that we already defined. So we know gradient descent is going to take an x, and it's going to take a y, but then it's also going to take these three parameters from our initialization. And that's really all it needs. To predict then, we have this kind of interesting situation where we might fail. So what happens if someone tries to predict before they fit? Well, that's not going to go well. So in particular, while this is just illustrative, it kind of shows the problem is we might get an attribute error. Someone might try to do things in the wrong order. And really, this is what Scikit does too, is say must fit first. Got to fit before we can do anything further. But if we have fit this estimator, then all we have to do again is our function magic. So identity, if we're in the linear kind of a linear optimization, else, and now here we can't just use sigmoid. We actually have to do a little bit slightly more, and that's we want to round the sigmoid value. So the sigmoid will produce a probability. It will produce a probability between 0 and 1. So in this like kind of classification problem, it will produce either a number close-ish to 0 or a number close-ish to 1. But we actually want a 0 or a 1. So we'll round kind of the output of the sigmoid and then just cast it to int. And then finally, this sort of looks exactly like what we did before. We can return this function times x at now our betas, right? Our betas are just this coefficient that we have placed on the body of our class during the fit method. Okay, so that looks reasonable enough, but does it work? It's a good question. So we can try it in the linear case and say, we can fit x, y. And what we're hoping, right, is that the coefficients are the same as the linreg coefficients that we saw earlier. That was the goal. And we're good. And for logistic regression, we can kind of check the same. Of course, changing the kind. But we didn't really come for these coefficients. They do look good, modular rounding. But what we wanted to be able to do is predict. That's why we made this class. That's what we use scikit-learn estimators for, is we fit them and make these predictions. So how do we do that? Well, what we really want to make sure is that this is true. That all of these predictions are close to the predictions that were made by logistic regression. That's looking great. OK. That's really good. But now I want to go a little bit off the rails. And that's to say, when we were looking at this gradient descent method, I bet some of you in the audience were thinking, this really isn't much code. I bet this is tweetable. Well, unfortunately, it's not quite tweetable. But we're getting close. First we have to dispense with good engineering. So assertions, don't really need those. These betas are really just kind of neatly fit into that pipe. And this function, this function is valuable, but we really only use it once. We only use it in one place. And I bet you can all see where this is going now. But hypothesis, that's also used once. Loss, OK, but loss is just used once. And this gradient is kind of complicated, yes, but we only use it once. So this is starting to look not like a function, but a mere lambda. So we can make it so. And now we have this lambda. And guess how many times update step was used? Well, it was one. So a little formatting then. And we have this gradient descent method that still works. All right. But learning rate, the name is too good. Can't have good naming. So gotta fix that. And then how are we doing? So this is what matters, right? So this isn't my fault. This is Twitter's fault for giving us 258 characters. Don't blame me. So with my 280 characters, we're going to tweak this. So you can tweak gradient descent. And in particular, don't put this through code review. Like, that will not end well for you. But the point here is that gradient descent really isn't that complicated. While there are a lot of barbells that people have stuck on in the kind of the intervening 50 years, they're really just barbells. When someone starts talking about atom optimizer or stochastic gradient descent with restarts or like exponential decay of various hyperparameters, you'd think, I understand gradient descent. These are just barbells. Gradient descent itself, at its core, is a pretty straightforward, well, if not straightforward, a pretty well understood algorithm. And the heart of it, its core, is really, really an elegant and compact piece of code. So again, code review, not where this belongs, but the idea, kind of the notion that I want you to take away from this is that gradient descent, while people hype it up and contort it in various ways, in the end, it doesn't really come down to much more than this. So I want to thank you all for your time and open the floor to any questions if we have time. I think we have time for at least a little questions. Great. So the question was, with gradient descent and linear regression, are there problems that you can handle with this kind of like gradient descent linear regression that you can't handle through the normal equation, the closed form solution? And the answer to that is, in theory, no, but in practice, yes. The closed form solution, the normal equation solution, requires inverting x. So we have an x prime, x prime x inverse term. And x prime x is a really big matrix, potentially. If we have trillions of rows, say, in our design matrix, then this is kind of an n-cubed operation, and we won't be able to do it. There are no computational methods for inverting that matrix. In that case, we resort to something like gradient descent, which never requires a matrix inversion.
Quick follow-up. So is there anything we shouldn't do with gradient descent that we can?
So the question was, is there anything we shouldn't do with gradient descent that we should instead favor the closed form solution, the normal equation?
Or check if the gradient descent makes sure it gives us an answer. But.
Yeah, if you have a small matrix that can be inverted in a timely manner, I'd say there's no huge benefit to gradient descent. If you do, though, have like an online problem, so a problem where you have streaming data, you don't want to kind of like re-invert kind of the matrix now that it has one new row. Like, do the whole thing again. One thing that benefits gradient descent is it can be done quote unquote stochastically or in batches. So if you have batches or single elements of data coming in, instead of having to kind of like reinvent the wheel, recompute the whole solution again, these streaming data can just be another batch, and you can update the beta slightly. Exactly. Mm-hmm. All right, well, thank you all for your time.